Okay, let's start. Okay. It's my great pleasure to welcome you all to today's BrainLink X Lab Day talk concert. I would like to also welcome our guests of honor, Professor Yaoushing Yao, and also Professor Tristan Collins. This event is part of a 3-day conference that is going to be held at UNIST later this week. And this event and also today's talk concert is generously sponsored by the Ministry of Science and ICT here in Korea, as well as the Korean Federation of Science and Technology Societies. Before we start our talk concert today, let's watch a short video introducing the programs that are supported here by the COEF ST. Okay, let's start the video.
Amidst the world's rapidly accelerating changes and competition, what kind of future are you preparing for? We are chartering a path to the future through science and technology exchanges, bolstered by international cooperation. In this era, where scientific and technological competitiveness is directly linked to a nation's diplomacy and security, the power to overcome such challenges lies in international cooperation that fosters synergy through collective efforts, and from talents who will shape the forthcoming era. The scholars of the world are gathering in Korea. A platform that facilitates exchanges between Korean and international scholars, as well as between seasoned and emerging researchers, is taking shape. BrainLink X Lab Day, organized by the Korean Federation of Science and Technology Societies, aims to be a global hub of talent. By consistently enhancing and expanding the global talent network, we're laying the groundwork for a brighter future. By inviting global scholars, X Lab Day provides an opportunity for young Korean researchers to glean insights from the vast knowledge and experience of both Korean and international scholars, as well as to engage in collaborative research. In 2022, the inaugural X Lab Day saw a total of 14 meetings across various technical fields. Altogether, 449 individuals participated, comprising 70 from overseas and 379 from Korea, all aiming to build a stronger network in Korea and abroad. This year, for our 2023 X Lab Day, we have the honor of having Yaoushing Yao, professor at Tsinghua University and a Fields Medal winner; Philip Kim, a globally renowned professor at Harvard University, known for his research in graphene; Yoon-Sung Hwang, professor at Stanford University and Hoam Award winner; and Humboldt Research Award winner Zhigang Suo, professor at Harvard University, leading discourses of their respected fields. This year, the discussions will span 12 national strategic technology fields pivotal to Korea's advancement, including quantum mechanics, nuclear technology, and AI. The event will see the participation of 30 Korean and international scientists and engineers. With 2 organizers leading each technical segment, the gathering will foster in-depth academic exchanges, encompassing the sharing of recent trends and information in core technology fields, in-depth discussions on research findings, and the sharing of ideas. The focus of X Lab Day is connectivity and sustainability. Following the event, communities and clubs will be established based on each X Lab Day session to ensure ongoing dialogue among attendees and promote collaborative research. To ensure that today's dialogue becomes the seed for tomorrow's magnificent achievements in scientific and technological development, COAST, supports the reinforcement and expansion of the networks established through XLab Day. COAST, the organizer of XLab Day, stands as a beacon for Korea's science and technology society. Established in 1966, its mission has been to safeguard and amplify the rights and interests of scientists and engineers. Our endeavors extend to enhancing the public's grasp of science and technology and furthering its development through comprehensive policy research, planning, surveys, and consultations. As Korea's largest science and technology network with over 600 affiliated organizations, we are committed to promoting domestic and international cooperation and exchange. In the transformative era of the Fourth Industrial Revolution, where science and technology spearhead groundbreaking challenges, COAST remains dedicated to its role as a facilitator of scientific and technological innovations. In this era of technological dominance, we will navigate through the fierce competition by fostering global cooperation in the fields of science and technology. BrainLink XLab Day aims to broaden both domestic and international talent networks and become a global hub of talent. By making XLab Day into an event that scientists and engineers worldwide eagerly join, we intend to elevate Korea's global standing and bolster national competitiveness. Global Talent Hub, BrainLink XLab Day.
Okay, thank you for the video. And again, we are very grateful for the continuous support by the Ministry of Science and Technology as well as the Korean Federation of Science and Technology Societies. Okay, so let's continue with our event. Let me welcome again, with my greatest pleasure, Professor Shin-Tung Yao. I think it's a great honor to welcome you here in Korea. And Professor Yao is, I know him since 2015, and he's at the moment an emeritus professor at Harvard, as well as in Tsinghua University. He's also the founding director of the Yao Mathematical Science Center in Tsinghua University, the dean of the newly established Crescent College of very talented math students in Tsinghua University, as well as the founding director of several math institutes around China. I know him as a person who is famous for making the positive energy theorem with Richard Schoen many years ago, as well as for proving the Calabi conjecture, for which he received the Fields Medal in 1982. Obviously, his work in mathematics and beyond mathematics in mathematical physics, theoretical physics, has been paradigm shifting, but not just in academics and research, but his now recent involvement in establishing new research institutes around the world is making a very big difference in academic research as well as in our field of research for the new generation that is going to come in our field of research. Today, it's an honor to have you here, Professor Yao, and you will talk to us in your plenary talk about your recent book entitled Gravity of Mass, How Mathematics Rules the Universe. And this is a book that you wrote with Steve Nadis. And there you explain your rich life in both mathematics and how you shaped really a whole entire field of both in mathematics as well as in physics. So it's a great pleasure to have you here, Professor. Please start your talk. Thank you.
Thank you, Reg, and I'm grateful to be invited for this program. And in the movie, I saw two of my former colleagues in Harvard. Philip Kim is still in the physics department when I was part of the faculty. So I'm very pleased to see them here. When I came to Korea many years ago, I still remember in 1991, with my whole family. I had a very pleasant visit, and I was enjoying see the culture of Korean, and very similar to China in many ways, and I was very pleased to see them. And I've been coming to Seoul several times by now. Probably this is number fifth. And I met many Korean mathematicians and physicists, and we tried to hire some of them to China, but all of them are very loyal to Korean. They all come back to Seoul or to Korean later. So I really admire their loyalty to their own country. Anyway, so I'm going to talk about this topic called the gravity of math. It's based on a book that I wrote with Steve Nadies, who has been a collaborator for a long time. So gravity of math is really trying to explain general relativity from the point of view of a mathematician. There are many books about gravity, but most of them are written by physicists, and they seem to ignore the important contribution by mathematicians. So I'd like to explain some of them here. So first of all, this is a picture that I just arrived in Berkeley as a young kid, I guess, 20-year-old. And I was standing in front of the tower of UC Berkeley. I did not think much of gravity at all. I was only interested in math. And so I thought I would stick with math only for a long, long time. But then, of course, things changes, because once I see the mature development of many fields in physics, which influenced my thinking in mathematics. So that's very important for me later. When I start to think about in mathematics, the major concept for me is geometry. And geometry is a subject that I'm really deeply interested in, especially with the concept of curvature. And I learned curvature when I was in undergraduate, but only superficially. Once I arrived in Berkeley, I learned much more about geometry, and then I'm interested to understand curvature of space-time, because gradually I found out that in gravity, curvature is a major fundamental concept for Einstein to explain the force of gravity and also the matter distribution. Well, I did not really know what space-time was at the beginning, and then I started to learn from the students and from the teachers there, and I started to realize that special relativity, which was invented by Einstein and Poincaré together, was actually a fundamental beginning of modern physics. In a 1905 paper by both Einstein and the work of Poincaré, really changed the outlook of physics in 20th century. The fact you have a Lorentzian group, and Lorentzian group is dominating what space and time mean. So this is very important for me. And well, of course, special relativity describes the physics of systems in a uniform motion and a constant velocity. That already changed the subject of physics already. But it's considered special because it does not include accelerated motion. A key premise at the heart of special relativity was Einstein's insistence that the speed of light is constant. And this is extremely important because that is the building block of special relativity. A beam of light transmitted from a moving train won't travel any faster or any slower than light emitted from a stationary source. That's an important discovery due to the Morley-Michelson experiment in 1878, I think. Well, Einstein actually began contemplating this scenario when he was 16, and it was a starting point for the theory that he formulated a decade later. But a lot of the work of great men starts when they were very young, and so this is very important. And you see, this is a picture that was used by in all books in special relativity, a stationary train and a moving train. You see the light speed is the same. Well, in 1907, Einstein came to realize that all natural laws except the law of gravity could be discussed within the framework of special relativity. So gravity is very important because gravity, as formulated by Newton, was actually in contradiction to special relativity. Because in special relativity, information it can only travel within a finite speed. But in Newton's formulation of gravity, information traveled instantaneously. So this is a contradiction, inconsistent. So it's very important. Two extremely successful theories need to recognize each other. And that's what Einstein tried to do. He wanted to find a reason for the two great theories inconsistent, how to find out the problem. Well, so he tried to understand in the idealized case and generalize it to systems that are not in uniform motion with respect to one another. So it is this fact that starts the subject of general relativity. This is a paper that he looked into that. So this is a starting point of general relativity that replacing uniform motion by accelerated motion. And I think this is very important. So in 1907, Einstein had a conceptual breakthrough that is called the equivalence principle. Although this concept went back 100 years before him, starting by Galilei and Kuiper and Kepler and all those and all them. But Einstein was able to formulate it in a form that is important for modern understanding of gravity. So he established an equivalence between acceleration and gravitation. So a man is falling, say, from the roof of a house, as you see in this picture, would not feel his own weight, as Einstein put it, nor would he feel the presence of a gravitational field. That's because the falling man is accelerating, and that acceleration would exactly counteract the sensation of weight he would otherwise feel due to gravity. So this is a thought experiment. Nobody suggests you to do the experiment yourself. Anyway, that's one of the major breakthrough, conceptual breakthrough for Einstein. Well, once you recognize the equivalence between acceleration and gravity, then Einstein knew that he had to extend special theory of gravity, relativity to include accelerated motion, so that he would have a theory of gravity. So this is a very important conceptual breakthrough, that in order to understand gravity, he has to understand accelerated motion. And the fact that all the physical law has to be invariant under observer, whether you are on a uniform motion or accelerated motion, is a very, very important concept. Actually, in a way, it dates back to Riemann, who proposed the Riemannian geometry, which basically said that the important concept in geometry should be invariant under different observers. So in other words, if you choose a coordinate chart to measure geometry, it should be the same if you use a different coordinate chart. This is a rather important and spectacular breakthrough in geometry. Before Riemann, everything is depending on coordinate. And after Riemann, things should be invariant under coordinate system. Without Riemann's work, I don't think Einstein could create his general relativity. It was rather mature by the time when Einstein wanted to develop into general relativity. The major maturity of Riemannian geometry is just about right to be used. So it's about, I would say, 80 years before Einstein, the theory of special Riemannian geometry. But anyway, Einstein has a teacher. His teacher's name is Hermann Minkowski, where he learned geometry from him in ETH in Switzerland. Minkowski, on the other hand, thinks his former student is a lazy dog. He rarely attended his class, and he did not hand in homeworks. Most of the homework was held by Einstein's friend Grossman, which actually played an important role for general relativity later. So Einstein actually know not much mathematics during the time when he developed special relativity. But Minkowski said that this student of mine, who is a lazy dog, make a major breakthrough in physics, namely special relativity. So he thinks very highly of that achievement, of course. But then Minkowski, in 1908, developed something extremely fundamental and spectacular for physics in modern days. In 1908, he gave a lecture in Cologne, in Germany. He made a very profound announcement. He said, from now on, space by itself and time by itself will recede completely to become mere shadows, and only a type of union or two will stand independently on its own. This is a very famous statement which many people attribute it to Einstein, but it was actually started by Minkowski, and it is this statement that really changed the concept of space-time. It is this statement that physicists start to go from 3 dimensions to 4 dimensions. So physicists before Minkowski is thinking physics is only on a 3-dimensional world. But once Minkowski pronounced space and time has to be depending on each other, then we are looking at 4-dimensional space-time. This is not a trivial statement, because once you go to 4 dimensions, the freedom is much bigger. Without the freedom of 4-dimensional system, general relativity would not work. So this is very important to know that from then on, so according to Minkowski, what is being dealt with here is that the world in space and time, in a certain sense, is a 4-dimensional non-Euclidean manifold. So he actually put it in a practical term. He was the one who wrote down the so-called Minkowski metric. He demonstrated everything in special relativity can be understood through the Minkowski space-time. The flat space-time, we call it. In a way we look at it now, after 100 years, it looks trivial. But I think it's a very, very major conceptual breakthrough, that everything in special relativity can be described by geometry alone, namely by the Minkowski space-time. And this is something that even Greek mathematicians like Poincaré did not realize. After Minkowski did his Greek work and gave a geometric description of special relativity, so it becomes 4-dimensional space-time, Poincaré said that, well, it's fine, but I still prefer 3-dimensional space description. It's more down to the earth, so to speak. But of course, Poincaré died in a short time afterwards, so he did not realize how the whole thing developed. And unfortunately, Minkowski himself died. also. After he pronounced this whole thing in 1908, he died 1 year later. So he would not be able to see or carry out what he wants to do. So his student Einstein continues the development. And well, Einstein accepts the fact that the framework to describe general relativity, namely a theory that combines special relativity with gravity, has to be in a four-dimensional framework. And then by doing some thought experiment, he realized that one cannot use a scalar to describe gravity. You remember in Newtonian mechanics, the equation of gravity is a scalar equation. That equation was actually not due to Newton, it was due to Laplace and Lagrange and all these people. Anyway, now Einstein realized that that equation is not enough because now you are dealing with four-dimensional space-time, and by implementing special relativity, you found out you need to use a concept called tensor. This is very important breakthrough, that you need a tensor to describe gravity instead of scalar. But Einstein really do not know what tensor is. He has to ask his friend Grossman to find out what tensor is. So he knows roughly what he needs, but he does not know what is the mathematical background to carry that out. So he knows tensor is what he needs, but then he wants to imitate what Newtonian equation means in terms of tensor. So Einstein gets his friend, Marshall Grossman, a classmate of him, who helped him to do the homeworks in ETH when he was a college student. So he knows geometry better than him. So Einstein told Grossman, you must help me, otherwise I will go crazy. So then he wanted to find it. He told Grossman he needed a geometry in which the choice of coordinate would have no bearing in physics. That's because he knew that acceleration or not acceleration should be give the same equation for the gravity. So this general covariance, which is a way to rephrase equivalence principle, is a basic principle in general relativity. And this statement motivates the formulation of tensor and motivates the formulation of the equation of motion. So Grossman did not know this geometry either. He, at the insistence of Einstein, Grossman went to the library and then dig up what is known. And they found out what is known 60 years ago by Riemann. So it consists of tensor equations and all that. And Grossman warned Einstein, this is far more complicated than what you can handle. He thinks that physics cannot handle nonlinear equations, especially a big system. So he said, you should not be involved with that. But Einstein is much more insists on what he wants. He's not scared of, but he needs a lot of help. So this ground breakthrough geometric ideas come from Riemann, as I said. And Riemann actually was trying to do the same thing as Einstein wants to do. The trouble is that Riemann did not live long enough. He died when he was 39, and if he lived until 60, he would have known the experiment due to Morley and Michelson, that light speed is constant independent of choice of frame. And this prevents him to develop special relativity and general relativity. So now it's Einstein who understands that. So Riemann's work was extremely famous, and Gauss was extremely happy by this work. It was presented in his thesis in 1954 when he was 26 years old. You should know that Riemann already learned how to do experiment. He has done some experiment in electromagnetism in the famous physicist lab, Weber. He measured the Weber in the lab. So he has experience with physics. So in writing this paper, he actually is interested in understanding what space-time is. And he was even asking the question, what is the difference between very, very small distance and very, very big distance? He thinks that one should use different geometry to describe them. And this nowadays we call quantum geometry, which is still not understood. But Riemann already asked that question. So he found a new way of thinking about the curvature of high-dimensional manifold, including the four-dimensional space-time, that becomes the central to the field of general relativity. So he extends the non-Euclidean surface pioneered by his advisor, Gauss. Gauss was very old when Riemann became starting to do research. Gauss was 70 already by that time. So he did not teach Riemann that much. But he did do something I think is extremely important for Riemann, although Riemann never mentioned it. Namely, Gauss introduced the famous Gauss curvature equation, which says that it depends only on the metric and not depending on the ambient space-time, on the ambient space. This is very important, and Riemann exactly developed it to arbitrary dimension and independent of how the manifold sitting in Euclidean space. And this is extremely important. He introduced the Riemann curvature tensor, Riemann. Riemann did not publish the paper on Riemann curvature tensor in 1954. In 1858, he involved in a competition in the academy in Paris about some problem, mathematical problem about heat distribution. So Riemann is not rich. He wants to make some money by joining that competition. So he wrote down a way to understand heat distribution by using tensor calculation. In that paper in 1858, he wrote down Riemann curvature tensor, the full curvature tensor. Of course, once you have full curvature tensor, you know what connection means. The whole theory of Riemann geometry was already developed by Riemann. But he did not write down in great detail. He has many disciples, and many of them actually reside in Italy. There were Christopher, I think is in Göttingen, but there are Richard, there are several people, Bianchi and all that. All of them basically was inspired by Riemann's ideas. And Riemann got very sick when he was 36. He has to go to Italy every winter to avoid the humidity and the cold in Göttingen. So he spent a few months each year in Italy, in Milan, in Pisa, in Rome. He was eventually buried near Milan. So all this inspiration has been important for the Italian geometers. So anyway, he invented the concept of curvature tensor already. Well, this turns out exactly what Einstein did, though he had been aware of Riemann's work until Boltzmann brought it to his attention. So Riemann already considered the possibility that the structure space could be affected and curved by the presence of matter. He thinks that the space we inhabit may be a curved manifold, like in this picture shows. So he was aspired to devise a unified theory that tied together the laws of electricity, magnetism, light, and gravity. So unified field theory, so to speak. Of course, he does not know the nuclear interaction yet. Strong force and weak force was not known to him. But already he wanted to devise a theory that unifies all this theory. In fact, both Gauss and Riemann contribute in a very substantial way to the subject of electricity and magnetism. In fact, Riemann already wrote down the equation of wave equation for magnetic wave. And he knew that the magnetic wave travels according to light speed. So he has made a lot of important contribution already. Well, as I said, he did not know the Michaels and Morley experiment, and also, unfortunately, he died prematurely in 1865 due to TB. And this is very unfortunate fact because he was probably the greatest mathematician as far as I can tell. In a matter of 15 years of his life, he created many, many different subjects in mathematics and in physics. Well, then, of course, Richard and Levi-Civita carried Liemann's ideas not much further. Inventing the field in more detail, introduced tensor calculus, and Grossman then learned these ideas and taught this to Einstein. He brought the tools to him. And Richard and Levi-Civita generalized Liemann's idea, translated in a framework that could be put exactly in the way that Einstein needs. So the metric tensor is now becomes a replacement of the field equation of the Newtonian gravity. So the potential in Newtonian gravity was a scalar. Now it is replaced by Gij, which is the gravitational potential of the new field. Okay? Then, according to Newton, or according to Laplace, you need to differentiate this potential 2 times to get something interesting, namely to become the matter distribution density. That's what Newtonian mechanics told you. So naturally, you get a tensor to be a potential. You want to differentiate it 2 times. But after differentiate, you want to make sure what you get is still a tensor. Now, with this constraint, it turns out there's no choice, but you get into concept of curvature. When you differentiate the metric tensor 2 times, you will get into curvature. That's how curvature is defined. But the end result should be a tensor. So there's not much choice. Namely, you have to go to curvature tensor. And now it's a rank 2 tensor, so to speak. There's actually no choice, but you get into a concept called Richard tensor. This was introduced by Richard in 1900, about 15 years before Einstein wrote down his Einstein equation. So in 1912 and 1913, Einstein and Grossman collaborated and devised a theory of relativity. So Grossman, being a mathematician, a classmate of Einstein, was involved in building the theory of relativity in a substantial manner. He was a co-author of the first paper that Einstein developed. Although Einstein kicked him out later, after 3 years, when he wrote down the actual equation, but the equation that Einstein and Grossman wrote was very close to the actual equation. And this paper is called an outline paper. They show how gravity could arise from the curvature of space-time caused by the presence of matter and energy. Einstein wrote the physics part of the paper, and Grossman wrote the mathematics part. I think Einstein still do not quite understand mathematics at that point. But after 3 more years of struggle, he understands much better. But at this point, I don't think he understands it that well. So this was a good start. But there are 2 drawbacks. First of all, Einstein and Grossman were unable to make their equation fully covariant. So it still depends on the choice of coordinate chart, which is certainly not good. And Einstein likes to use a coordinate chart where the determinant of the metric is equal to 1. And it's very funny that happens. But anyway, they actually did not succeed to write down the final equation. And on the other hand, they want to convince themselves that this general covariance was not possible in any case. Therefore, what they wrote down is good. So almost just like a boy who want to convince themselves studying is not important, it's impossible, it's better not to study. So that's what they prefer to say. We cannot achieve coherence because it's impossible. And this in a very funny way, because when Einstein started field of general relativity, the guiding principle is coherence. But now they see they're getting closer, and they decide, well, we cannot achieve it, we gave up. That's what the attitude is at 1913. It's all well recorded. It's not, I did not make it up. Einstein wrote it down clearly in that way. Second of all, the equation did not correctly predict Mercury's anomalous orbit. That had been a key deficiency in Isaac Newton's gravitational theory and provide the motivation of Einstein to create an entirely new theory. So after Newton developed the Newtonian mechanics, he was extremely successful in calculating the motion of planets. Everybody was so excited about it. But then they missed a really small part, namely the Mercury was moving in an orbit missing by very, very tiny angle. And no matter how they tried to correct it, they could not correct it. So the astronomers and the physicists start to question what to do. And so Einstein and some others thought that one needed a new concept. And so new concept was develop a new equation of motion that will circumvent this problem. So they did a calculation numerically and didn't succeed to recognize this problem. So Einstein felt that he did not succeed because he did not come up with the right calculation. I think many people believe that is the case, but I believe actually Einstein did not do the numerical calculation correctly. The approximation he used, I'm sure, was wrong. Because the equation that he used later was actually the same equation in this special case. In this special case, they assumed the scalar curvature equals 0. In that case, the Grossman-Einstein equation is actually the same as the one was created in 1915. So they claim that they did the right prediction in 1915. There's no reason that they did not do it right here. Anyway, I think it's very interesting for the historian to take out exactly what Einstein did in terms of calculation, because he do approximation numerically, and I think he probably did not know how to do it correctly. Anyway, Einstein collaboration with Grossman ended shortly after this paper, and he then derived from other mathematicians. And he began an extensive correspondence with Levi-Civita. Levi-Civita, as I told you, learned geometry from Richard and from Riemann, and they wrote a paper, interesting enough, in 1900, and was published. And the Einstein famous equation, Gij, Rij minus R over 2 Gij, appears in that paper. Only in that paper, the first time, we know this gives rise to a conservation law. And Einstein missed this last part. And Levi-Civita was corresponding with him without telling him what he's supposed to write down. So although Levi-Civita knows the right equation, but he was thinking all in terms of geometry. He did not tell Einstein what he needs, what the error he needs. But instead, Einstein was interested in creating an action principle. The action is in terms of integral something, which is not scalar. Einstein thought it was a scalar, which will be independent of choice of coordinate, but Levi-Civita point out the scale, the function that Einstein chose depends on choice of coordinate. And it shows that Einstein was rather ignorant of what's going on in geometry. He insists on it for a long, long time, for a few months. And he has corresponded with Levi-Civita, arguing why he was right. And finally, I think he gave up. Einstein gave up, and so is Levi-Civita. Levi-Civita felt that it's difficult for him to explain the right idea to Einstein, and Einstein felt that he cannot understand Levi-Civita. So he conceded that his proof is incomplete, Einstein. So he wants to look for other people for help. Now, by the way, this Lagrangian formulation, Einstein finally in 1916 wrote to Hilbert, said that now he will realize why he was wrong, that this is not a function. So he eventually Einstein admit that he made a fatal mistake in this thing. Anyway, so he gave up the correspondence with Levi-Civita in June 1915. Einstein went to Göttingen, the capital of mathematics in 19th century, to meet Hilbert. He wrote to Hilbert and Hilbert asking help, and Hilbert invited him to go to Göttingen to explain what he needs. This was June in 1915. So in Göttingen, and Einstein told Hilbert what he needs, the field equation of limited covariance. So what does limited covariance means? He wants to insist the determinant of Gij to be equal to 1. So he wants to choose special coordinate. But in his conversation with Hilbert, and also Felix Klein, who happened also to be a faculty in Göttingen, he becomes much more aware of the fact that the equation needs general covariance. And this was something he needs to overcome. Well, Hilbert was then interested in this question of gravity. He invited Emil Noether to come to Göttingen to work on this problem. So by the end of the summer, which roughly in September of 1915, Hilbert figured out the equation according to all the records that we know. He found his own version of this general relativity equation, which he arrived by different methodology, and this independent choice of coordinate, which is satisfied the equivalence principle. And then Hilbert told Einstein he found the equation. Einstein got very upset because he felt this is a domain that should be completely cornered by him. And Hilbert invited Einstein to visit Göttingen, and Einstein declined the invitation, decided that he will work on it by himself. So Einstein proposed to give a 2-week seminar in the Persian Academy. After the first week of presentation, he found out he could not overcome the difficulty. He wrote to Hilbert asking for help by postcard and asking what the equation is. Hilbert replied with an equation sent to Einstein. Einstein acknowledged he received this postcard. But anyway, in November 25, Einstein submitted his paper for publication, the correct equation of motion for gravity. But actually, Hilbert already submitted his paper a few days earlier, in November 20. This is a proof of his paper. It's called the Foundation of Physics. So Hilbert was very ambitious. He called this the Foundation of Physics. Maybe the title was too ambitious, and I think this got Einstein really mad. And Einstein was cursing him everywhere, actually. And there's no question Hilbert wrote down the action principle, integral scalar curvature, and also he wrote down the equation of motion. But then apparently in the proof, Garlic proof, he changed the equation a little bit. And then historian claimed that Hilbert never finished his paper on the right time and copied from Einstein. I think this is total nonsense, because there's no question that Hilbert wrote down the action principle, and which is followed by everybody. And Einstein never wrote down the action principle. He only modeled after the equation of motion and wrote down the equation. But anyway, I think it is clear that, to say the minimum, the equation was derived independently by Einstein and Hilbert. And Einstein may arrive here slightly later, but he knew the meaning of physics of this equation, although Hilbert also understands the physics meaning of the equation too. They have been, you should look at their papers, both of them. Well, he was very much inspired by Einstein, so I think it's probably fair to call it Einstein equation. But the action is certainly due to Hilbert. Now physicists try to change it and call it Einstein-Hilbert action. So what is the equation? The equation looks rather simple in disguise. This equation, Rij minus half R times Gij equal Tij. The left-hand side is the curvature of the tensor, and the right-hand side is the metatensor. So what does this equation look like? This equation is a simple, well, I won't say simple, it's a clear generalization of the equation of gravity due to Newton, which says Laplacian of the gravitational potential is equal to the matter density. So matter density corresponds to Tij, and Laplacian of the potential corresponds to curvature. This is how Einstein motivated himself to write down the equation, because Rij is exactly like Laplacian of the metric. Now, when Einstein and Grossman wrote down the equation, they did not have R over 2 Gij there, because they motivated it in a way just using Rij looks like Laplacian of Gij. They forgot that conservation law has to be satisfied. Namely, Tij satisfies the conservation law, the left-hand side also has to satisfy the conservation law. So Rij cannot be equal to Tij alone. So you must add in some terms. This term actually, as I mentioned, R over 2 Gij was known to Bianchi and known to Lütschid and Levi-Civita 15 years before them. And actually, Bianchi knows this term in 1880, so 35 years before Einstein. But they do not know how to interpret it in the correct way. They knew this whole term because they know this whole term together satisfies the conservation law. Well, conservation law is very important, both in geometry and in physics, and so it's consistent, satisfies conservation law in geometry. That's what the geometer knows, but they did not know it's related to gravity, the conservation law in gravity. Anyway, this is one of the most spectacular equations that appears in general relativity. The right-hand side is matter, the left-hand side is the geometry. So geometry is inspired, I won't say dictate, is motivated by the right-hand side. And the right-hand side has to connect with the space-time together. So this is a very interesting equation, but notice Tij could be identical 0, and still there is gravity. So matter could be identical 0, and yet space-time could still be curved. This is something that does not occur in Newtonian mechanics. So Einstein, at the point wrote down this equation, he felt he has understood gravity completely at the time when he wrote down the equation. But he did not realize that just an equation does not mean you can solve the equation. Because when you have an equation, you need to have several data to support it. Namely, you need to know the boundary condition, you need to know the initial data. These two problems borders physicists and mathematicians in the last 100 years to find the right boundary condition, to find the right initial condition. Otherwise, you cannot predict anything. Okay? So this is a fact that Einstein did not realize at the time when he wrote down this equation. He thought now QED, everything is done, but it's not done. Anyway, so there are many people, as I said, as early as 1880, people already know all this thing. So Einstein did not know this work of the previous people, but in fact, even Hilbert did not know this in a funny way. He derived it himself. But at the back, one should know that M. Noether was actually playing a very important role in the whole subject general relativity. I was told that Hilbert actually invited her to be one of the co-authors, but she declined. And she then understood how equation of motion can be determined by symmetry consideration. And so this is very important. She arrived in Göttingen in 1915, and he wrote his great famous paper in 1918, where he tells you how symmetry dictates the equation of motion. Now, many people attribute this to Einstein, which is really not fair, because M. Noether was the one who actually formulated it correctly, and is being used all the way up to now. Okay, so this equation tells you a very important statement, which paraphrased by John Wheeler, who was a physicist in Princeton. He says space-time tells matter how to move, and matter tells space-time how to curve. So, but matter is not as important as the space-time curvature, because matter could be trivial, as I mentioned. Tij could be zero, and yet space-time could still be there and curve. And this is a fact that is very important. Namely, Tij equals 0 still gives rise to important calculation. This is actually a very complicated equation. There are 16 equations on all. Only 10 of the equations are independent of each other. You have to figure out how to choose the right way to count the equation, because the equation is supposed to be independent of choice of coordinate. So you have to mod out the choice of coordinate. And finally, there are 10 independent Einstein equations. It happened to be nonlinear partial differential equation. It's very difficult to solve. Up to now, only a few cases were solved completely. In general, we have no idea how to solve this equation in a closed form. We know how to deal with one body problem, namely a spherical symmetric data or axially symmetric data. But when we have to deal with two bodies interacting with each other, nobody knows how to solve it. Not even numerically, I think. Although people did produce some solutions, but I don't trust that completely. So, anyway, this nonlinearity caused a lot of trouble. Massive object, curved spacetime, which generates the things we call gravity. But gravity is also a form of energy that can cause additional curvature of spacetime. That creates even more gravity. This is what we call nonlinear phenomena. It creates more problems and keep on propagating. Now, the equation that Einstein spent nearly a decade was complicated, and he did not know whether any exact solution could be found. And this did not bother him at the beginning, but once it is found, it bothers him tremendously. But it turns out Einstein was very lucky. Practically a few weeks later, after Einstein's paper was published, a German physicist called Schwarzschild found this paper, and he just left his job as a director of the Astrophysical Observatory, and he went to the German army during the World War I. So he was in the front of the war, and he spent some time to look at this equation. He assumed a simple thing, assuming there's a spherical symmetric star. And then, well, that's the best hope to solve it in this simple case, namely spherical symmetry. And then she's found a solution exactly. So based on spherical symmetry, they know everything depending only on the distance from a point, namely r. And now this simplifies the equation tremendously. It becomes an equation depending on t and r only. No more t, x, y, and z. 4 variables is too far more complicated. And then Schwarzschild's solution explains the spherical symmetric case. So as I mentioned, Einstein was using numerical way to solve the equation, which I think is non-accurate. But then within a few weeks, Schwarzschild found the exact solution, and then you can calculate the prediction much more accurately. So Einstein was saved, I think, by this solution, which is explicit and can be found in an exact manner. And then you can use this one to do calculation, to do experiment in terms of observation. So Einstein's paper and so Hilbert's paper was submitted in November 1915, and Schwarzschild provided solution in February 1916. This is really fast speed. And he found a mathematical description of the interior of spherical cell. Well, in doing that, he found a rather amazing finding. If the star's mass was packed into a small enough volume, when the radius r equals 2m, m is equal to the gravitational constant times the total mass divided by speed of light square, then within this cell, not even light could escape the star's intense gravitational pull. That's what Schwarzschild found out. So in a spherical symmetric solution, there's funny thing going on near the origin of the cell. And there, even the light could not escape. Well, then this becomes a very funny thing, and physicists work on this one for a long, long time. The density and pressure could approach infinity at this point, and later on, this object is called Schwarzschild black hole. The radius 2m is now referred to as the event horizon of the black hole. So the sphere with 2m as the radius is called the event horizon. Einstein believed this is total nonsense. This star with this property was just an artifact created by those abstract mathematicians who do not really know what they are talking about. So, well, even the famous astronomer who did the fundamental observation to verify Einstein's theory, Eddington in England, he said there should be a law of nature that to prevent a star from behaving in this totally abstract manner. So the concept of black hole was not well received. In fact, the concept of black hole was not well received all the way until 1970s, in the late 70s, in fact. I was a faculty in Princeton, IAS. There are a lot of astronomers who told me what you're doing is useless because a black hole does not exist. In 1923, George Birkhoff, who is a faculty in the math department in Harvard, proved a rather important theorem Namely, he proved that any spherical symmetric solution for Einstein equation is always Schwarzschild, independent of the boundary condition or initial condition. This is a very strong uniqueness theorem that many physicists, even some Nobel laureates, did not believe that is true. Even now, I was debating with some of them last year. Well, anyway, Birkhoff proved that the gravitational field outside any spherical symmetric distribution of matter is uniquely described by the Schwarzschild solution to the vacuum Einstein field equation when we assume Tij equals 0. So, well, as I said, Einstein was not convinced. He published a paper in 1939, rather late, that says Schwarzschild singularity do not exist in physical reality. So, in short, Einstein did not believe black hole. Well, one of the criticisms is that Schwarzschild black hole cannot be real because they do not spin, and nothing could be perfectly spherical symmetric, and this never appear in nature, so therefore they are against it. So then people look for a non-spherical rotating black hole, which is much more realistic, and this is amazing, takes a long, long time, until a New Zealand mathematician, Kerr, who found it later. But before that, let me say, many people tried very hard and found out many special properties if it exists at all. And Roy Kerr actually found it in 1962, and he makes some assumptions, but the assumption worked out by creating the solution. He assumed the black hole would rotate at a uniform rate, and also instead of spherical symmetric, he assumed it's axially symmetric, so reduce the equation still more. This is an assumption which is not making it easier, but Kerr actually finally submitted a paper in 1963 in Physics Review Letter. This is probably one of the most fantastic solutions of a nonlinear system or equation that can be written down in closed form. I think this is probably historically the major solution that can be found by human being. Most of the solutions we found are numerical, but here he actually found one which is not only spectacular, but actually useful. Almost all the astronomical predictions are based on this equation. And I found that funny that he did not get the Nobel Prize based on this. In 1975, the Nobel Prize winner, Chandrasekhar, who I met in Chicago, he praised Kerr's contribution. He said that in my entire scientific life, extending over 45 years, the most settling experience has been the realization that an exact solution of Einstein's equation of general relativity discovered by the New Zealand mathematician Roy Kerr provides an absolutely exact representation of untold numbers of massive black holes that populate the universe. So Chandrasekhar himself wrote a big fat book, about 500 pages book, to give a detailed description of the Kerr solution. So it shows that how important he thinks this whole thing is. And of course, Chandrasekhar made an important contribution to the rotating black hole himself. Well, after this discovery, there comes another mathematical breakthrough made by Roger Penrose, who got a Nobel Prize 3 years ago, which I think Kerr should have been included. Unfortunately, he was not. Well, in 1965, he wanted to study whether the Kerr singularity is stable or not. So once a singularity or black hole is formed, is an important question is whether these things are stable. That means when you perturb the initial data a little bit, then the singularity still persists. This is a subject that, of course, all physicists want to know. You don't want to say that you create solution which by kicking it a little bit, the singularity disappears. So stability of singularity is extremely important. Otherwise, whatever is found is not useful. So in 1965, he considered an interesting thing. He wanted to ask the following question in the absence of symmetry. He wanted to say that the K black hole or the Schwarzschild black hole are not created because of symmetry consideration. He said, let's forget about symmetry. Maybe you can find a way to control the collapse of matter. And so without symmetry, can we create singularity? So Penrose brought in tools from geometry and topology that had never been applied to problems of this sort. He created a very famous work called singularity theorem, and this was cited in his Nobel Prize winning citation. He proved that when something called a closed trap surface is formed, the collapse to a singularity is inevitable. So Penrose suggests that in order for singularity to form, you just need to create something called closed trap surfaces. So what is that? Closed trap surface is basically a surface whose extrinsic curvature is so extreme that light gets trapped inside. This surface area shrinks to zero during gravitational collapse. So does the volume. So that's what he wants to call a closed trap surface. Well, this surface exists in the Kerr metric, space-time metric. And also, do a small perturbation of the Kerr metric, such a closed trap surface still survives. Therefore, in perturbing the Schwarzschild or the Kerr metric, closed trap surface exists and singularity will still exist. So this is very important. So Penrose proved that the presence of a closed trap surface will eventually to lead to the formation of a black hole. But he did not spell out how a closed trap surface can be formed. It's artificial said that once it exists, a singularity will form. This was actually proved by me and Rick Stern in 1979, where we proved that a closed trap surface is formed when the matter density of region exceeds the critical threshold value. This was published in 1983 in Communications and Math Physics. This is the first paper actually demonstrate a black hole can form under a physical reason. Namely, when the matter density is bigger than a critical value, a black hole forms. And Penrose did not prove this statement. Penrose said that if a closed trap surface is formed, then black hole forms. But here we prove that if the matter density is bigger than certain critical mass, it will form. So then, after many years, after 20 or 30 years, black hole actually can be found experimentally, and I think many of you knows it, and is believed to exist now. And this prediction was rather accurate. It took a whole century to confirm, and I think finally the theory of general relativity found is based in a firm ground, both theoretically and experimentally, and this is very important. And then, of course, there's a question of cosmology, where Einstein's equation will introduce lambda. I do not have time to go into the explanation of cosmology, but this whole theory has been fascinating, and many, many mathematicians and physicists has been involved in the last 100 years, not just physicists, which was misleading. And this now is a very fruitful and rich subject, where many physicists and mathematicians are involved. So I will stop here today. Thank you.
Thank you so much for the very interesting talk, Professor. I think because of time constraints, we will move on to the next talk, and then we will have a quick discussion session where we will take some audience questions regarding your talk, Professor. So our next speaker is Professor Tristan Collins from MIT. And he's going to, I know him since his work on case stability of Fano varieties and his work with Professor Yao. And he's going to talk to us today about stability of bundles and partial differential equations. Please go ahead, Tristan.
Okay, well, thank you very much. It's an honor to be invited to speak here. So I'm going to talk about sort of the other side of the story, if you like, of this mathematical description of the fundamental laws of physics. So as Yao discussed in his talk, so there are four fundamental forces in the universe. There's the strong force, the weak force, the electromagnetic force, and gravity. And so we've just heard from Yao about the theory of gravity, so I'm going to try to discuss the other three in this list. So these three theories are all described by something, by geometric objects called vector bundles, and associated with vector bundles there's a notion of gauge theory. And then, as Yao has just told us, the gravitational force is modeled by a sort of different animal called, which is manifolds and metrics. So these are these sort of underlying objects for the mathematical theory of gravitation. So, so a manifold, for those who don't know, so a manifold is basically a space that looks locally like flat space. So we live on a manifold, right? Here we are in this room. It looks locally like a giant piece of paper. You could imagine we're standing on a giant piece of paper. But of course, globally, there's more complicated structure. So globally, we know that, well, despite some common objections these days, we know that the planet is a sphere. We live on a giant sphere, but locally it's sort of indistinguishable from a sheet of paper. And of course, you could imagine also living on a gigantic donut or something like that. So that's what a manifold is. It's just a space that looks locally like a flat space. And a metric G, as we've just learned, is a way of measuring sort of distances between points in some generalized sense. So given a metric G, it gives us a manifold a shape. So once we know how far apart points are, this space begins to take some shape. And the theory of general relativity can be roughly summarized as prescribing, based on sort of physical grounds, what the shape of space has to be. So it tells you that the metric G, which is this sort of determinant or way of determining the shape of space, has to satisfy some partial differential equations, which are the Einstein's equations that just appeared in Professor Yao's talk. So the other side of this story involves vector bundles. So roughly speaking, a vector bundle over a manifold is just an assignment to each point in M of a vector space describing the possible configurations of some system. So there are lots of these vector bundles that we experience in our day-to-day lives. So for example, two that I can tell you about right now are the two-dimensional vector bundle, which describes all the possible directions we can move on the surface of Earth. So I'm standing at a point on Earth. I can move in any two-dimensional, I can move in a two-dimensional array of directions. So that describes a vector bundle. And there's a bigger vector bundle, which is a three-dimensional vector bundle that includes the possibility of jumping off the surface of Earth, right? Moving in the upwards or downwards direction. I guess also digging a hole. So, but in physics, there are many, many, many other important vector bundles that arise in these descriptions of the fundamental forces, which are not just these two that I've described. So a gauge theory is a theory which is, so instead of a metric, we're given a connection A, which you can think of as some sort of potential for the field strength. And it allows you to say that a vector here, so at the point that I'm standing, can be identified with some other vector at this other podium. So the connection is some way of identifying vectors from point to point on a manifold. So associated to a connection, there is something called the curvature. So it won't really matter so much for us, but there's this expression. You see that the curvature looks like a derivative of the connection. So this is kind of familiar from physics, that the field strength, right, Fa is like the field strength, is the derivative of the potential. So you can imagine that the connection is some version of a potential for a gauge theory. So just as general relativity prescribes the shape of space, a gauge theory prescribes the connection A. So again, there's some energy functional. So Yao was talking about the Hilbert functional in general relativity. So I've learned that it's not the Einstein-Hilbert functional; it's the Hilbert functional. So in a gauge theory, one typical requirement is to put an energy functional, which is the sort of the integral or the total norm of the field strength. So this is a Lagrangian, and this Lagrangian, so in this case it can be viewed as some sort of nonlinear analog of the Dirichlet energy. So you can imagine, so for functions, right, if you integrate the norm squared of the derivative of a function, that's called the Dirichlet energy. It appears in the descriptions of electromagnetics. And critical points of this functional, or the functions that satisfy the Euler-Lagrange equation, are exactly the harmonic functions. So from this functional, one expects to extract some notion of a harmonic, sort of harmonic, in quotes, connection on a vector bundle, which we hope is some model for fundamental physics. So in this case, the critical points of this functional are called Yang-Mills connections, and these turn out to be very important in the description of these three non-gravitational forces. So typically you also fix. So there's also a choice of a Lie group, which appears here, or Lie algebra, and so typical choices of Lie algebra, especially for sort of describing the standard model, are unitary and special unitary groups. Okay, so now an important question arises, which we have to address, is if we're given a vector bundle and some choice of a gauge group, right, SUN or UN, when can we find a Yang-Mills connection? So if you want, so just like Yao was discussing this sort of importance of the Schwarzschild solution or the Kerr solution to general relativity, if you want to say that you have a physical theory which you can make predictions or calculations, you have to have examples of these objects. You have to know that they exist. I mean, if you're describing a theory for which there are no solutions, you're not describing a very interesting theory. So this is a very hard problem. So just like the equations of motion and general relativity are very, very difficult to address, similar issues arise when you start studying this Yang-Mills theory. So in this theory, right, the set of connections, the set of A's is some wildly infinite dimensional space. You can imagine it's like the space of functions or something like that. I mean, it's even bigger than the space of functions in some sense. While the set of critical points or solutions to this functional is some finite dimensional in general, or even empty set. So this equation is describing some enormously high codimensional set inside of a very infinite dimensional space. So finding these Yang-Mills connections is an incredibly transcendental. It's a very, very difficult problem, right? In typical situations, solutions of the Yang-Mills equation, or really any geometric PDE, won't even be expressed in terms of the sort of standard functions that we experience or learn about in any mathematical class, right? These are sort of very, very transcendental objects. So in particular, these equations that arise just like the theory of relativity are nonlinear partial differential equations. Okay, so they're very highly transcendental. So how do we know that solutions exist? So luckily we have a very beautiful and powerful theorem due to Donaldson and Uhlenbeck and Yao, which produces for us many, many examples of these objects. And this is what I want to try to describe, because the ideas that are introduced in this theorem of Donaldson, Uhlenbeck, and Yao have really come to play an incredibly prominent role in mathematics in the last 30 years or 40 years. So the power of this theorem, which I haven't stated yet, but which I will come to in a moment, is that it relates this sort of very infinite dimensional problem, which is highly transcendental, to an algebraic problem, which amounts to checking a sort of essentially finite list of inequalities. So it's some enormous reduction in complexity from a highly transcendental nonlinear partial differential equation to an algebraic problem, which can in practice be solved in examples. So this algebraic problem, right, if we can solve it, is sort of a much more finite dimensional problem, and if we can solve this problem, then we conclude that we have one of these Yang-Mills connections, and hence a sort of model for a gauge theory. So let me tell you about this theorem. So a Riemannian manifold, we were just discussing general relativity. Roughly a Riemannian manifold is some sort of, you can imagine some sort of setting in which gravity can be discussed, right? So this is a theory in which this is a sort of, roughly speaking, I mean, we want Lorentzian signature, but you can imagine taking some sort of product. Anyways, this is a sort of, roughly speaking, the Riemannian geometry is the background for gravity in some sense. And so one of these manifolds is said to be Kähler if it has what's called a parallel complex structure. So that means that it has a map from the tangent bundle to the tangent bundle which squares to -1, and which is constant from point to point. So in fact, the Earth has one of these complex structures, which is just taking a cross product with the normal vector. Right, so this complex structure allows us to identify this manifold locally with the complex numbers rather than the real numbers. And so we can talk about holomorphic vector bundles, so some special notion of some vector bundle with a special structure. So these Kähler manifolds also have what's called a symplectic form, so it comes from just composing the metric with the complex structure. And so this being symplectic means that its top wedge product is a volume form and it's declosed. So symplectic geometry or symplectic manifolds are the setting for classical mechanics, so Hamiltonian mechanics, right? That takes place on a symplectic manifold. And so a Kähler manifold is in some sense the intersection of gravity, so Riemannian geometry, classical mechanics or quantum mechanics, which takes place on a symplectic manifold. And then this extra structure of an integrable complex structure is somehow associated with generalized notions of symmetry, so supersymmetry, these kinds of things. So these objects are really all fundamental for physics, and Kähler geometry is the place where all of these structures meet and live. So it's an incredibly important and very highly structured setting for studying geometry. So suppose that we have a holomorphic vector bundle. So a vector bundle, I mean, all of these structures live on the sphere. So you can imagine that this is all taking place on planet Earth, which is a Kähler manifold. So to any connection, say with a unitary gauge group, we can associate a number called the degree of E, which comes from, so you take this curvature tensor, which I wrote down, or curvature form, which I wrote down before, you just take its trace, so this is now a differential form, and I can wedge it with this Kähler, or this symplectic form, and I can integrate that over the manifold. And that gives me a number, which turns out, after dividing by 2 pi I, to be an integer. So this is the theory of Chern classes. And it turns out, this sort of very important fact is that this number is just an invariant of E. It's some integer, so 1, 2, 3, -1, -4, but it has nothing to do with any of the choices that we made. It depends, it depends on this symplectic form, at least in cohomology, but it does not depend on the choice of connection. So it's some invariant of this bundle, right? So it's measuring some sort of topological information about this vector bundle. Okay, so here's the theorem of Donaldson, Uhlenbeck, and Yau. It says that if you have one of these compact Kähler manifolds and you have a holomorphic vector bundle, which is sort of not a sum of smaller pieces, then this bundle admits a Hermitian Yang-Mills connection if and only if the following algebraic condition holds. So you take every holomorphic, roughly speaking, every holomorphic subbundle of E, and you just check this list of numbers. So you take the degree of S, which is this number that we wrote down before, and you divide by the rank, which is just the dimension of S as a vector space. And that number has to be smaller than the corresponding number for E. Okay, so in practice, the number of holomorphic vector bundles is, I mean, this is a relatively small relative to the sort of space of functions. So this is a sort of small list of inequalities between numbers, right? This is saying something like 1/2 is less than 1. So, so this is something that you can really get your hands on in examples, right? And this is the kind of thing that you could, in theory, check if you're given a relatively explicit example. So, and this list of algebraic inequalities for numbers, right, is equivalent to the existence of this Yang-Mills connection, which is something that you could never hope to write down in practice. So in this case, we say, so this is associated with algebra geometric notions of stability. So in this case, we say that E is slope stable. So the Donaldson-Uhlenbeck-Yau theorem is this equivalence between an algebra geometric condition called slope stability and existence of solutions of PDEs. So it's really difficult to overemphasize the beauty and power of this theorem. So this, when I was a beginning graduate student and I learned this theorem, it had an enormous impact on me. But I think, I mean, beyond the fact that it gives this sort of equivalence between something which seems sort of easy in some sense, this sort of list of numbers that have to be ordered, and the existence of a solution to PDEs, which, if you have experience with PDEs, even writing down solutions of PDEs in 2 or 3 variables in a domain in Rn is incredibly difficult. So this is a really amazing theorem, and it's had an enormous impact on mathematics since. So that this theorem appeared in the mid-1980s, and since then we've sort of come to understand that the principles underlying this result are really foundational to many problems in geometric analysis, especially in Kähler manifolds, and especially those which come from sort of physical problems. So there's this sort of guiding principle, which is to try to relate algebraic notions of stability with solutions of nonlinear partial differential equations in the context of Kähler geometry. And so there are many prominent examples beyond the Hermitian Yang-Mills setting, where these correspondences are known to exist. So with a very recent example being the existence of Kähler-Einstein metrics, which is due, of course, to the fundamental work of Yau and more recent work in the case of positive Ricci curvature due to Chen, Donaldson, and Sun. So, and this was a program that was really initiated by Yau shortly after the work with Uhlenbeck on the existence of Yang-Mills connections, which has recently, sort of in the last 10 years, come to a sort of fruition. But recently, I mean, studies which come from physics, right, these ideas which sort of arise in physics, and especially the study of mirror symmetry and string theories, has led to a sort of proliferation of new problems which are guided by this principle of an equivalence between algebraic stability and solutions of nonlinear PDEs. But these are really new and very interesting and difficult conjectures which correspond which concern correspondences between algebra geometric stability conditions and solutions of new sort of challenging nonlinear PDEs. So one example or two examples are the Thomas-Yau conjecture in the theory of sort of symplectic geometry, which is supposed to relate the existence of certain special submanifolds with notions of stability on something called the derived Fukaya category. And recent works that I've been doing with Yau and with some other collaborators on understanding this sort of mirror problem to this, which is the so-called deformed Hermitian Yang-Mills or Lung-Yau-Zaslow equation. which is another equation that arises in mirror symmetry as an attempt to describe sort of, roughly speaking, the particles that you would see in a type 2b mirror symmetry, or type 2b string theory. So in these examples, we're really at the sort of beginning of this story. So in these examples, in fact, we don't even really understand the notion of stability, which is appropriate for these problems, because it becomes very, very complicated, and somehow it has to encode, in some sense, it has to encode all the possible particle dynamics that you would see in a type 2a or type 2b string theory, including sort of particle decay and many sort of complicated phenomenon, which have to somehow interact well with these various algebraic structures on spaces of things called D-brane, so that it becomes sort of enmeshed with structures in derived algebraic geometry. So it's a very interesting and very sort of exciting new story, but somehow it's all motivated by this sort of principle that was introduced by Donaldson and Uhlenbeck-Yau. So these are very exciting, incredibly rich, beautiful structures, which were only at the very beginning of understanding. But it's a very exciting direction for the future, which is sure to involve sort of input from many different areas of mathematics and theoretical physics. So it's a very exciting time, I think. So I'll stop there. Thanks very much.
Okay, thank you so much for the very interesting summary talk, Tristan. Now we are going to start the short discussion session where the audience is free to ask us questions, and we will also have a general discussion session regarding the two talks that we just heard. Okay, I would like to thank Professor Xin-Tung Yao and Professor Tristan Collins again for the beautiful talks. As a starter, I actually, because Professor Yao gave us a very beautiful summary about the interaction between mathematics and physics over the last 200 years, basically, and how that led to major developments in both mathematics and physics. And Professor Tristan Collins kind of summarized the latest developments in that interaction, leading up to developments even in string theory. So I would like to first ask Professor Yao, you yourself, you made major contributions like the interaction between Einstein and Hilbert. You have worked with, like for instance, Professor Richard Schoen, who is going to come to Ulsan tomorrow, and also your proof of the Calabi conjecture. Could you give us a very 2-minute short summary of your experience of interacting with physicists, and also your experience of making major contributions to the field?
Well, first of all, I was interested in mathematics because it's such a beautiful and elegant theory that mankind can develop. After 2,000 years, mathematics is far more mature than those days, and I found that extremely beautiful. So I was led to go into mathematics, especially in geometry. But then I found out a lot of theory in mathematics are inspired by physics in the old days and in the modern days, especially general relativity and lately string theory. And not only they are related, but it actually gives many key steps to inspire how mathematicians should move. And I think this is extremely beautiful because the intuition created by looking at nature in a different manner could create something that can be proved. And this is very exciting. It's almost like magic. You base on some abstract reason, and you believe something is true, and finally we can prove it. Well, proof is not something abstract, I consider, because it's is really something nobody can change once we know how to prove it by logic. And this creates confidence for mathematicians, of course, but also to physicists. I think if physicists keep on creating things which cannot be done by experiment, and even can be done by experiment, it cannot be 100% correct because the question of how strong the energy level and there are many speed, for example, in Einstein's theory, speed when it's close to light is very different to slower movement. And so there are constraints on experiment. But mathematics is something based on logic only. It cannot be wrong. And this is a way that gives a 100% confidence for physicists that something they are talking is not nonsense. And we see many theory end up to something that can neither be proved by experiment nor by mathematics. And in those cases, something is very fishy. But now with mathematics supporting the subject in physics, I think it's very useful. Of course, string theory is still far apart from nature that we can observe, but there are many parts of physics we can verify, either by experiment or by mathematics development. It cannot be achieved by luck only. It has to be some truth to it. That's why I found it fascinating.
Yes, and in fact, Tristan's talk actually exemplified the current state of the research that is going on with mathematics and also string theory and the broader physics community. These days, there's a lot of hype of young people going into engineering subjects or AI. Quantum physics or quantum information is quite a big buzzword these days. So from that point of view, what do you think are the fruitful contributions of mathematics and the interaction between mathematics and physics what kind of contribution can this fruitful symbiosis between those two fields can contribute towards these new areas of science that are buzzing up both in Korea and around the world? And what do you think? How can we contribute towards this development? That's a question to both of you.
Well, AI is a very important subject because it does indicate something seems to be true, but it's similar to physics. I mean, you predict something, an experiment proves that it's right, and AI is something we kind of make some guess, and it comes out to be right, but it has never been proved why it works. And this is dangerous at the same time because there's always some chance what they suggest is wrong. If we come to something that's a question of life and death, for example, driving an airplane or a car, and if something is wrong, all the people can die. When you come to that, you better be very careful. And we have experience in the history of mathematics, even in mathematics. The Italian geometers developed algebraic geometry in an extremely beautiful and fruitful manner, but then they are missing a lot of cases that they should pay attention to. They did not, and after 50 years, the subject encountered a great tough time to go on. A new concept was introduced using more algebraic methods, and this led to the development by Zariski and also by the Grothendieck and Andrew Wei, and this revolutionized algebraic geometry itself, and then explained many things that was not able to explain by the Italian geometers. What the Italian geometers do are still as important as before, except now we understand it much better. And I feel both theoretical physics and AI are playing a similar role as what the Italian geometers do. They see something which is beautiful and even useful, but whether we can explain it just based on what we know is far away from clear, and we need some new conceptual breakthrough to understand them. And we are in this period that we need to introduce new concepts to understand what is being studied in industry or in experiment. And I think it's fascinating that mathematicians should play an important role now.
Yes, I fully agree. How about you, Tristan? What is your opinion?
I agree with Yao completely. I think that, in my opinion, the solutions to the hardest problems are always based in fundamental science. So if you sat down as an engineer and tried to produce GPS without knowing the theory of general relativity, it would be an impossible engineering problem to solve. And somehow that advance is based in the solution to a problem which it was never, I'm sure Einstein and Hilbert never intended to build GPS. They were solving a problem in basic science, and it had as a consequence enormous advances in engineering and technology.
Yes. Are there actually also additional questions in the floor?
I have a question about the talks. First of all, I really appreciate the talks. The ideas that were presented, I've probably known much like 30 years, but a lot of things were very confused for me over the time, and the talks really clarified many things for me. I wanted to ask a question. Yao brought up in the talk that when we go from Newton to Einstein, or space-time, Minkowski space-time, there was a breakthrough, and we're solving these PDEs. So we have these objects, but now the next stage, you were talking about boundary conditions and initial conditions. And when I think in the Newtonian space-time, where space and time are independent, then I understand initial condition very well. But in the context of the space-time, when space and time are mixed together, do these concepts have to be revised, boundary condition and initial conditions? And is this, that's maybe like a technical question, but are we waiting for another breakthrough in this area, like in solving these PDEs using, are we waiting to discover the right formulations of the boundary conditions or initial conditions?
Well, first of all, in general relativity, we do not have a global time function. So formulation of initial data will be involved, how to make the choice of time function to be consistent. This is a gauge dependent. There are several gauges. One is how to choose a time function, and then the second one is a choose of the space coordinate correctly. Of course, we know roughly what to do, but those things are very complicated. And so far, it has not been shown to be extremely effective. And the numerical solution has partially successful, I think, but I would not say it's very efficiently carried out. So, boundary condition is, right now we are looking at an object in an infinite space, so that at infinity, we know it should be asymptotically trivial. Thus, we are looking at some isolated physical system. If we are not looking at isolated physical system, the boundary is interact with the other sub-object, then we really have to choose the boundary condition correctly.
That's the theory of solitons, is it?
Well, soliton, not really. I mean, the soliton, we assume infinity is somewhat understood. But now, if you take two black holes interacting, for example, what is the initial condition for the two black holes? And infinity is presumably we choose to be asymptotically trivial. But if you have, say, 3 black holes interacting, one black hole may be escaping to infinity, two of them are interacting, then the boundary condition is changing near infinity, because you have to capture the other black hole running out. And then at the same time, you still have to keep the two black holes interacting to be intact. So the boundary conditions becomes complicated in that case. There are people, physicists, who simply choose a fixed boundary condition, which is clearly wrong, because the black hole which is escaping to infinity are forced numerically to bounce back. And this, of course, gives you a wrong result. The black hole, one black hole could certainly escape to infinity. We cannot simply choose the Dirichlet boundary condition near a large black hole, a large radius. Okay? So it will bounce back. So the choice of boundary condition becomes subtle, and truth of initial condition is a very important question in cosmology. How does the universe start? If you do not choose the right time they start, the evolution would be completely different. So this is another problem that I think Hawking and many other people keep on thinking about. Hawking wants to propose a theory with no initial condition. And, well, it looks nice, but I don't think it's working as ideal as it's supposed to be.
Thank you for the answer.
Okay. Are there any other questions in the audience? Yeah.
Okay, so you reminded us about great contribution of mathematicians in early, late 19th century,
Yeah.
including Einstein tensor, which I was not aware of, and how those great discoveries have been, some sense, not communicated to other community. I guess physicists, at the time, number of theoretical physicists are very small, so.
Well, the answer is very simple. Riemann was motivated to do general relativity. I'm pretty convinced. You read his paper, he's keep on talking about space, times, and all those. But he died in 1865, to be precise. Then these other things were discovered in 1880 to 1900, when these are disciples of Riemann, but they are not focused on understand the physical background. They are more interested in the geometric background. So they only care about geometry. As a result, what they know is extremely important geometry, but not used to understand general relativity. If Riemann was still alive, I think he would, but he did not. So that's what happens, I think. So as I said, the Morley-Michelson experiment, I think, was found in 1880 around. If Riemann lived until 65, she would know this experiment, but she did not. He did not.
Okay. I think we are now running out of time. So let me thank again Professor Xintung Yao and also Professor Tristan Collins for the very interesting talks. And also I would like to thank the audience for coming to this event. And thank you again, everyone. And we thank also our hosts here at the CoFST. Thank you.